Okay, this video is going to be about the rotary encoders, and it's also going to be my first ever Arduino project. I've never messed with this before. We'll see how it goes. I got, for one thing, I got for this project was a breadboard from SparkFun, and it's pretty much an Arduino Uno board, and seems to work pretty well. They say one of the advantages, it has the FTDI USB chip on it, and which they say is more reliable, and I guess that's so. And it's also got a pre-installed LED on pin 13, which like I say, I'm kind of new at Arduino. I'm very new at Arduino, and I don't know if that an LED on pin 13 standard or not. I know that's what everybody does their blinkies with. But anyway, it's a pretty nice board. It's got nothing on the has nothing on the backside, no traces. It's smooth as a baby's butt, and so I've got it fixed to my little breadboard here, and it's on there pretty good. And I've just got, it just has a tack down with a loop of wire here at this hole, and one at this hole. I don't know if you can see these, and one at this hole right there. So that kind of holds it in place. And then I'm using the USB power 100%. Of course, everything at the switch is passive, and I'm bringing the 5 volts and ground over here to the switch. And you can see I've got some stuff going on here, and this is for plugging in just a bare Atmel chip, which I'm gonna play with get to a little bit later on. I don't know if this video or after. The switch itself is just the rotary encoder. I got it from SparkFun also. It's got the three LEDs, red, green, blue. It's got a push button in it. It's got 3 leads on one side, 5 on the other. The 5 here are ground, the LED common, and the 3 LED leads and a switch lead. And the other side is the actual A and B rotary encoder output. They're on the ends, and the center is the ground connection. So, and this is the same guy. It's under here, this knob. I got the big knob in order to try to rotate it real fast for testing purposes. So I got that press on knob, and it presses on pretty well. And probably not the strongest thing in the world, but it'll do for this. So this is the one we'll be using. Now I got the software I didn't write. I got it off of the forum. I guess a guy goes by JARS, I believe. J-A-R-S. Wrote this not too long ago. And so I'm going to try out his code. I made a few changes. Some scope. I got some scope signals in here to see how long interrupt takes, and to see how long the print takes, and be looking at those in a little bit. And to run the code, I guess nothing much is going to be happening here. We'll be moving over to the screen, which unfortunately I'm going to have to shoot off the camera shot off the screen, because I don't have my FFmpeg to do a screen recording on my development machine. So we'll be going over to the to that machine, and then looking at the Arduino monitor for outputs. But one thing we have here it's going to help is this knob has a little mark on it, so you can get its orientation. This switch is 24 detents to go completely around. So this will help us when I go turning the knob as fast as I can. We must always end up at a multiple of 24 on the count that this thing puts out, and so that'll help us do that. So then let's go ahead and run this thing and take a look at what it does. Okay, so here's our Arduino IDE. It's not too terribly bad. It lets you use an external editor, which is great, which I couldn't stand to use this one, and it's pretty good about that. And otherwise I haven't had much chance to explore very much of it. As I say, this is my first project ever using the Arduino. So anyway, we got the monitor. One thing I had to do to get the monitor up is change the my groups where I was a member of the dial-out group. If you do a long listing on dev TTY USB 0, you'll see it's in the dial-up group, and on my machine anyway. This is a Slackware box. So I had to put myself in the dial-up group, and I had to change the preferences.txt file for Arduino to make the serial output dev/TTY USB 0. And it took a little while for it to accept that. I had a little trouble. It was plain and obvious in the text file, and restarting it a few times finally took hold. So I don't know what was going on there. Probably driver problem, user problem. But anyway, so let's run this guy. Okay, so now I'm going to go around the turn the knob around one time. And that should be 24. And we got 24. So we've got to a count of 24. And if I go backwards, just counterclockwise, 24, we should get to 0. And we do. So then we got back to 0, which is good. And if we go further counterclockwise, it counts negative. And that should be a negative 24. And that's a negative 24. And then if we go back to clockwise, back to 0, it zeros. So that's working pretty good. It's tracking pretty well. Now let's go real fast and see if we can defeat it. So I made 3 revolutions, 72, and we're at 67. So we did lose some. So that's turning it, pretty quick, and probably faster than you ever would. But it will miss some counts that way. Let me hit reset to get back to 0. And we get our prompt, and I'll try it again to go real fast. There's 2 revolutions, so we should be at 48. We're at 44. So you can't go too fast for it, but it's really kind of impractical. Depends on what you're doing. If you're normally turning it on an instrument, it should be fine. If you have it attached to a motor, you have to watch out. Sometimes people make their own encoded steppers or whatnot by attaching one of these rotary encoders, and you can drive the motor too fast, it looks like. And another test I want to do is to move it off of detent, but not to the next detent, and move it back. In other words, you just decide to turn it clockwise, say, And just about as you start, you change your mind, you want to go counterclockwise. So it leaves the detent you're on and does not make it to the next detent, but you change direction. Let's see what that has to do with it. So there we got, I turned it slightly right and went back to 0 and it counted -1. Did it again clockwise, just a little bit before it got to the detent, and went back to 0 and it counted again. So it's not this is not a state machine is the problem. It's not tracking. It has to make a total from one detent to the other, or else it'll get lost. I can probably put it back to 0 now by starting to go counterclockwise and come back to 0 twice. Oops, went one too far. So that was never leaving a detent. Or maybe I did hit it once there. Anyway, so it looks like it has some problems, but that's very rare conditions. I'm pretty impressed that it does this well. Arduino code and C code, and you know, it's definitely usable. And so let's take a look and see what kind of noise this is overcoming and how the timing exactly works on this fella. Okay, let's take a shot here of some of this knob action. I'll give it a quick twist, and there we get some edges. Let's go over and look at our first fallen edge. We got the I guess the A on top, the B on the bottom. Oh, there's some pretty good noise on there. That's this guy here in the center. That's 10 microseconds per division. That's 11-12 microseconds. He looks like the longest guy, 12 microseconds. Got some other short ones. Let's look down at the next channel. Oh, that's 10 microseconds. It's 28 microseconds. That is pretty noisy. Let's look here. Wow, that's relatively clean. Going up. And what do we have? See, you had 28 microseconds for the longest. That's a good while. These are really short here. These are this is in the neighborhood of 200 nanoseconds. It looks like the falling edge. Is the falling edge the worst? Well, he's not bad. Maybe there's dirty spots along the dial. This one's clean. He's pretty clean. A little overshoot. A little crosstalk up there on the top channel. He's not too bad. The rising edges aren't too bad. There's another clean one. This is pretty clean after the first. In fact, I don't see much. There might be some. That's not bad at all. Oh, there's. Did you see that? I think there are dirty spots. Remember it said found 28 microseconds, the biggest one so far. That's 5 microseconds per 5, 10, 15, about 19 microseconds. Those are pretty healthy. Let me just get another trigger. Could probably spend all day looking at this stuff. You can kind of see where it's the line are thicker. There might be some noise. That's not bad. So it really looks like that's clean. It really looks like where you are on the dial position might be bouncier than others. That's pretty noisy there, but the duration's not very long. But none of that seemed to ever bother the count out of this code. So the code seems to be handling this pretty well. Okay, now I've got the interrupt on here, and I'm going to go real fast and see if I can make it miss a count. Give her a reset and see if we can see why it misses a count. So let me give her a high-speed spin. And let me check the monitor real quick and see if it did miss a count. Yeah, we missed one, so it's going to be hard to find it. Along the bottom is the interrupts. And you can see the way it's set up. It's interrupting off of a timer period. They're just real regular. They're set up to occur, it looks like every 2, 4, 6, 8, 10, every 1 microsecond, every 1 millisecond. So 1 millisecond, and then the interrupt itself only takes about 5 microseconds, 5, 10, 15, 7, 18 microseconds. In relation to the speed we're going, it doesn't matter that much. Now, where that missing guy could be is hard to say. Probably where an interrupt is real close to an edge. How about this guy? No, I think that's clean. Find some dirty pulses. Oh, huh. Maybe. No, I don't think he saw that. I don't see any other good. Of course, I didn't get how many to get. I didn't get many turns at all. Well, that could take forever. But I don't think any of the pulses come faster than the. It's hard to get a pulse to come faster than the period. So why it would miss, I don't know. Let me slow her down one. Get another trigger. You can take forever looking for something like this. The fastest pulse is down here. I'm sure I got fast as I'm going to go. It looks like he's doing a pretty good job of getting interrupts, two per 1 pulse period. You need to be in a quarter, have a hit in every quarter for sure to get them all. And maybe a possibility that you could miss that. This one, that's dead center. Well, to say exactly where you missed, yeah, we could look all day for this. So anyway, you can miss one, and that's its scheme. You might be interested in the print routine. I've got another high pulse during while the print goes out. Get back to 5 milliseconds. We can see the print. I've got the sorry about that. Got the bottom trace. That's the duration of the print routine. Oops, he jumped ahead, didn't he? And that is 20 microseconds per division. That's 1.7 milliseconds. And you see the print routine doesn't take much time compared to how fast you can turn the knob either. So yeah, I was expecting it to take longer than that, but I guess that's right. It's only printing out one number and coming right back. Well, a number and a carriage return. But it is scanning an array of multiple. If I had more than one rotary encoder on here, it scans an array of rotary encoders, but it still has to do the indexing, even though there's only one on here. It still has to do the index, read its value, figure out who he is, send that value to the Arduino monitor, and then print a carriage return and come back. Of course, some of that time for both the interrupt pulse you see and the printer pulse you see, some of that time is the set and clear of the pulse too, so you can knock off a microsecond maybe off each end. So anyway, not too bad. Now I want to go and use my other rotary encoder and see how it does on this program. Okay, now I'm going to do about the same set of procedures with a different rotary encoder. Here's this guy I got from my local surplus electronics store. There's no data at all on it. There's some silk screen. It's mounted on a board, a little PC board, with some pins of its own. So it includes resistors on the back for the pull-ups, so we don't need any pull-ups on the board. It doesn't have an LED. It is a switch. You maybe hear that. And basically it's real noisy. So that's what we want to use for testing, because this guy really bounces severely most of the time. Also, the knob we used before, the slip-on knob that I got from SparkFun, it's useful for the little positional notch there. It will fit on here, but this is a D. See if you can see that. It's meant for a hex screw to lock down on, and this is slip-on, and it's the right size for this knob, but missing half of the shaft almost. It doesn't grab real well, but it will work for our purposes. It won't take a lot of mechanical strain, so I'm not going to give it a lot of mechanical strain. So anyway, that's the rotary encoder we're going to look at now. Same software in the breadboard and we'll try to repeat what we did before. Okay, now we're going to try to repeat our tests we did with the previous rotary encoder. Let me get a reset. And we seem to be talking. Now I'm going to go around just one revolution here. Okay, now I'll go around one time. This is a 20 turn. Yeah, this is a 20 turn rotary encoder. Almost forgot to check that. Let me give it another reset. Okay, now I'll go around one time. And we should have 20. And we have 19. Let me try that again. Let's just turn a normal speed. There's 21. This is a noisier encoder. Reset again. Go backwards this time. That should be minus 20. Oh, this one isn't tracking very well at all. Okay, now let's go with the partial turn. I'm going to turn it clockwise, but not to the full detent, and come back to the original detent. So it should not be 0. It looks like I did go to 1. It's not as hard to hit the not hit the detent. I think that was messed up. Well, that's tracking that pretty well. I think oh, there's one. Count backwards. It's another clockwise partial. It did count back and went to 0. It counts backwards. So I'll try the other counterclockwise. It didn't register that. That was a full back and forth there. It didn't register. There, it did it right, and it counted back up. So that was a partial turn counterclockwise and returned to 0, and it counted. So it's just like the other encoder. It's not handling partial states, but those rarely occur and probably aren't a big deal. But if we can, we want to get this thing as close to perfect as possible. So we'll see what we can do about that in the future. Let's go ahead and look at the signals on this encoder and see what we're actually dealing with. Here we're set up to look at our noisy rotary encoder. Got channel. We got A and B on here. Let me do a quick right rotation, and that looks pretty noisy. Let's come over here. To the leading edge. Let's get some good spikes on there. Almost full amplitude. Those are, that is lasting 75 nanoseconds. A little bit over 75 nanoseconds for that longest one. That's pretty fast. Find another one that looks, look at this falling edge, looks like there's something there. No, here's a real, that's really goofy. Look at that. That's got a good long pulse. Really don't count that as noise. That's like not leaving the, that's like going back. I don't see how that happened so early. I spun it pretty hard. That's 10, 20, 30, 40, 50, 60, 64 range microseconds. That'd be hard to filter out. Let's see what we can find on the other pin. It's got a little bit of noise. It's not too awful bad. This thing is a lot more raggedy than the other encoder. Every one has some noise on it. That probably wouldn't interfere with anything there. Let's go down. Look at another one. Whoops. Where'd you go? Sometimes this Rigol needs to take advantage of some of this research we're doing here on their rotary buttons, because sometimes they jump around pretty bad. Oh, look at that. That is horrible. That is just horrible. It's strange how it's noisy and it settles down for so long and then continues jumping around. This position in turning the knob is only like 1, 2, 3, 4, 5, 6, 7 positions, and it was, there wasn't any stuttering. I just, spun it pretty smoothly, as fast as I could right at first. That's right in the middle. There shouldn't be any backing up. That's just a heck of a noise. That's 10, 20, almost 20. It's about 18 microseconds. Can you imagine filtering that out? We're going to look at filtering a little bit later. So this explains why this guy is messing up the code a little bit. It's pretty bad bouncer. Let's see if I can get what happens when I do a partial turn. There, I just barely touched it. I don't know what the code did, but that's what we're looking at sometimes. You just get off, you get a count. It's probably I don't know, it might be a real count. I'm not on, why am I not zeroed? What happened to channel? There we go. And I wasn't in a D10, I guess. You retrigger, just slight turn. That didn't even count 1. Oh, look at what we're looking at. Got a little bit of noise as it tried to leave. This is something, this moving it less than 1 detent even is probably something you'll very seldom do. But like if you just go and touch the knob, you say you're planning on turning it clockwise, and when you put your hand on the knob, that could move it, a little bit counterclockwise or vice versa, and then you turn in the correct direction. That could get you off if you're depending on exact counts. Now this is for like these knobs on the scope. You're really not going precisely to counting. You're just moving in the general direction, and you look at the value printed on the screen and you adjust accordingly, so you don't think too much about overshoot, undershoot. The only trouble with these Rigol knobs is the way they take off sometimes. So anyway, in human, depending on what you're doing, the application, you might get away with code like this. But that is just barely nudging. So you barely nudging the knob, so you can see what what could happen to you, and what we see what does happen. Look at that. That's that's pretty weird. That's strange right there that lasts so long at that mid-level. It's almost like a float, but it really shouldn't be able to float. That is very strange. This is a screwed up encoder. But then you have the issue of where, well, should I do I have to qualify all my encoders? Do I have to test them all thoroughly before I put them in my instrument? Will quality change over time as I buy them from different vendors? You know, those are the issues. If you have software that won't handle this stuff, those are quality issues. You're dependent on your hardware to solve for you. But we need to see, why is he not 5 volts? So those are the quality issues you have to, you know, you have to address in your hardware. You either make, you know, if you're gonna save money and buy variable quality parts, you need to make up for it somewhere, and the software is the place to do it in. And this is an example. Well, there's a nice little edge for this guy. See, most of the time, that's what's weird. It's not consistent. It's like the speed you go and places in the different places in the rotation might be different. See, none of these are really that terrible there. But, you know, if that's the case, that different places are worse than others and different encoders are worse from others, you got to compensate for that possibility happening 100% of the time. You know, worst case is what you have to design for. So now I think I'll try to get into looking at some filtering. A lot of people think filtering is the way to go. You know, put a capacitor on it. The only trouble, with filtering your noise is you're filtering your signal at the same time. So depending on your worst case noise, you can get in trouble. You can really slow down your leading edge of your regular waveform. So anyway, so it looks like need a little software improvement and a little approach improvement if you want to handle really bad encoders. Okay, now I've got the 0.01 microfarad capacitor across the A pin, and I left no capacitor on the B side so we can compare back and forth, see what signals generally look like. There's 10K on the pull-ups on the A and B on the little breadboard that this switch is mounted on. So we got 0.01 microfarad and 10K for a filter. And let's see what that does. And give her a spin here, and see if we can find some trash. And it's hard to say, you know, how big these pulses would be otherwise. You can see some of the looks like some extra roll-off in the signal itself. Let's see if we can get a measurement of that. Put it the base right there. That's 500 nanoseconds. I'm going to say about here is where we want our full signal swing. So that's 5.1/2, 2 microseconds. 2 microseconds rise time, we'll call it. Let's take a look at rise time on B without the capacitor. Oh, look at it. There's a good healthy glitch. We'll also put that on 500 nanoseconds, and that's what that's on. So you can see it's a lot faster. Already with 4 squares, it's going to be 1, 2, 3. That's 200 nanoseconds. 600 nanoseconds. That's a little over a quarter of the time. So that is affecting the rise time on your signal. So you got to be careful how much capacitance you put in, because the more you put in, this is your main signal, you're gonna create more time before it shows up as a 1. So so you have to be careful of that. Okay, let's get another trigger on here. See what we get to look at. Let's pick a guy at random. Well, here's some pretty good peaks. It's hard to tell how big these would have been, how long they it looks like they'd have been about 1.5 microseconds. We found some lot longer ones than that. Well, here's one, I guess you could say. Here's one that like didn't get filtered. That's a real long time. So that could cause an error. So you can find some noise on the unfiltered side. Now, small, looks very similar. Should be able to find something here to compare to. Oh, look at this. Oh, okay, here's some. So it's this guy. 1, 2, and a little over 2 microseconds. Didn't filter that out. Golly. Yeah, these are some big ones down here. That probably cause an error on the one side. These are all monsters. Filtered out a lot of the normal stuff, I guess. Well, so you can see. Oh, look at this dude. This is a beautiful square wave, just about. And that's 2, 4, 5 microseconds. Filter doesn't have much effect on that. That's another thing. What's typical of your part, and how much can you really count on that capacitor really doing that much? We could mess around with capacitors, you know, keep increasing the value, but you're gonna get, you know, roll off right here in your signal, your main signal, and you don't want to delay this too much. How much is too much? You know, we're sampling on interrupts that can happen anywhere in this time, so you could just miss this guy, and if he's narrow enough, you could miss him entirely. That could help you miss him entirely. So I guess we can conclude that our filter is doing some good. Not in all cases. See, that's pretty well filtered down. You know, you'd really be a long shot to hit that guy. I'd quit turning the long knobs here. This guy is about, it's 1, 2, just a hair over 2 microseconds. That would still be seen. That's above the high voltage level for the part. So there's a chance this is going to work better, but not always. Work better, but not 100% probably. So let's go look at the monitor and see how it counts. Okay, we'll take one last look at what this guy does with caps on it. I put another cap on the B pin, So I've got two 0.01 microfarad capacitors on here with two, each has two 10 kilo ohm resistors. So we've got filtering on both pins. So we'll see if that, it looks like it improves it a little bit. We'll see how it does here. I'll go one turn around, we should go 20, I'll count to 20. And before we had a few errors, there's 20. Now I'm going to go back to 0 and minus 20 all in one swoop. I think that's minus 20, yep. So that's counting pretty good. See it? I'll do a fast one here. When that ended up at 0, well, that missed some. That missed a bunch. I'm not at 0. There's 0. Missed 7. So the caps are helping somewhat. The low speed normal turning, but they're not reliable going really fast. That's, I mean, as fast as I can go with my finger on that knob. So well, let's try the let me reset again. Try the partial movement. That's clockwise, not quite to the first detent, and back to 0, but it counts minus 1. So that's going to do the same thing. The capacitors don't help with that. That's a logic problem. Okay, well, thanks for watching. I hope it makes some things real. Looking at the scope traces and seeing what filtering does and what problems would a bad rotary encoder looks like as far as bounce goes, and what a pretty decent one looks like as far as bounce goes. This is my first Arduino project. It's not that bad, but I don't think I'll be using it anymore because it's not. It's just not. It hides too much of the hardware from the developer, and you need to know your hardware and you need to know your code. And you know, once these I've been reading the forum on Arduino, and once you try to mix programs, mix libraries, then you have to start reading people's libraries and really understand. You might as well learn how to do it yourself and do it yourself so you know what's going on. I'll probably write a blog about Arduino, but you know, if it gets people into electronics and gets them excited about doing this, that's great. But once you've done that, you know, don't be afraid to read a data sheet. Don't be afraid to read a programming manual. You need to do. You're not going to find this out in business anywhere. You're not going to find anybody using Arduino to build products with, and they're not hiring people who only know Arduino. I'll tell you that. So anyway, thanks for watching. Next time we're going to look at the same thing, same two encoders. We'll look at a different program and check out state machines. Okay, bye bye.